So we will actually look into this chapter. Yeah, the first thing that we start is related to acidity. Yeah, acidity. We need to find out. Yeah, we want to compare the acidity of water, acidity of ethanol, phenol, ethanoic acid. We want to actually put them. Yeah, and then classify them. Which one is going to be most acidic? Yeah. So if you look at this, yeah, so this one we normally leave it first. Okay, we just leave it. Okay, we compare with the rest. Yeah, so we compare with ethanoic acid. So if you look at ethanoic acid, is C double bond O OH, and then you have CH3 over here, which is going to be a methyl group. Okay, if you look at this, okay, oxygen, okay, is going to be electron withdrawing group. Yeah, so the electrons will be withdrawn towards the oxygen over here, and then okay, the electrons are also going to be withdrawn from to the oxygen over here. Okay, so what happens over here is okay, the electrons, okay, they are going to become delocalized. Okay, where you are going to actually get something C double bond O, CH3, and then O minus. The electrons, they become delocalized over here. Okay, so this ion is going to be more stable. So this is going to form the H plus easily. Okay, or in another words, okay, you can say that the bonding, yeah, the bond between the O and H is going to be weakened, and you are going to have tendency to form more H plus. Okay, therefore, okay, carboxylic acid will take the top spot, okay, in the acidity. And when we look at phenol, yeah, when we look at phenol, okay, so phenol is going to be written in this way. Okay, so phenol, and you know that, okay, phenol also, okay, the lone pair of the electron, okay, at the oxygen, they have tendency to go inside. Okay, or we say that the lone pair, okay, of the electron, okay, they get overlap, okay, with the pi system. Okay, when they get overlap with the pi system, that is going to make, okay, this particular ion, which is the phenoxide ion, okay, O minus, okay, to be more stable. Okay, to be more stable. So you are also going to form the H plus. Okay, you are also going to form the H plus. But do remember, okay, the bond, yeah, the bond that is broken over here, because it is actually being withdrawn by two oxygen for the ethanoic acid, that will be the strongest. Okay, but phenol is going to follow up, yeah, the second, yeah, acidity. Yeah, still going to give you H plus, but not that much. Okay, and then the water, yeah, so we hold on to water first, okay, because generally water supposed to be the lowest acid. Yeah, the acidity of water is going to be the lowest. Okay, but now we compare with ethanol. Yeah, when you look at ethanol, ethanol is going to be C and then OH. Okay, and then you have CH3 over here. This is ethanol, and we know, okay, the same, okay, oxygen is going to be electron withdrawing group. Yeah, electron withdrawing group, they will pull the electron towards that side, similar to ethanoic acid. Yeah, similar to ethanoic acid, but the difference is, okay, the CH3 group is electron donating group. Okay, the CH3 group, the alkyl groups are electron donating group. So the amount of the electron that is actually being pulled towards oxygen is going to be compensated, okay, by the electron donating group. So that is going to actually make this bond not so weak. Okay, this bond is not going to be easily broken because it is attached to electron donating group. Yeah, the carbon attached to OH is attached to electron donating group. Therefore, the bond energy between the O and H is going to be high. Okay, it's going to be difficult to be broken. Okay, therefore, okay, you are not going to get the H plus. Okay, H plus is not going to be formed. okay, the ethoxide ion, okay, the ethoxide ion is not going to be stable. Okay, they don't
Where does the
form this.
electron?
Yeah.
What does that yellow arrow pointing towards the oxygen atom mean?
This
On
means okay, the
the
bond energy, okay, or the bond strength. Yeah, the bond energy is
yeah,
higher, slightly higher.
the one on top, sir, that yellow
The
arrow.
one on top, okay, is similar to this. Yeah, similar to this. The oxygen is going to be electronegative. Yeah, so they will pull the electron from the bond, yeah, the OH bond towards itself because it's more electronegative. So when they pull, yeah, it means the electron. If you look at it, okay, if O and H, if the electron supposed to be in the middle, yeah, when the electron is pulling, it means that the electron is going to be partially, it will go here, further away from the H. Okay, when it's further away from the H, it's going to be easier to be broken. Okay, so something like that. Okay, but in this case, okay, it's not going to be that further because it's going to be compensated by the electron donating group. So this arrow that I have drawn over here is simply telling that, okay, CH3 group is going to be electron donating group. Okay, when they are donating the electron, that doesn't mean they are donating to that carbon only according to the arrow. Okay, they are donating from here to here. The electrons, they don't stay there. Yeah, they are going to move. Okay, they are going to move, okay, to the place that it requires the electron. So they are going to compensate. Yeah, but I don't want to actually draw too much of arrow. Just I think this one is enough already. Okay, so this is going to, okay, this is going to be, so this ethoxide ion, okay, not stable. Okay, not stable. Therefore, this H plus is not going to be formed easily. Okay, so that will put ethanol to become the lowest acid compared to even with water. Okay, so if I want to put in comparison, yeah, from the highest acidity to the lowest acidity, okay, the highest acidity is going to be ethanoic acid, and then it's going to be followed by, okay, phenol, and followed by water, and finally followed by ethanol. So you need to learn about this. Yeah, so this is going to be, if you put it as pH, okay, the pH of ethanoic acid is going to be the lowest, okay, the lowest pH. But if you want to refer in terms of pKa and Ka, do remember weak acids we refer using pKa and Ka. So if I want to put pKa, yeah, pKa is also going to be similar to pH. pKa is the lowest over here. And then if you want to put it as Ka, Ka is going to be the highest over here. Okay, so you need to learn about this. Okay, so if I compare, okay, this pH is going to be higher. Okay, and the pH, okay, for a pKa, I think it's actually laggy in my iPad. Yeah, so let's actually wait for a while. Okay, but ethanol, okay, the pH is going to be higher. Okay, pKa is going to be greater. Okay, Ka is going to be lower. Yeah, so it's not reflecting over there. Okay, let me share the screen again. Let me Jordan. Okay, I'll share the screen again. So the part that I was explaining just now, okay, is the pH, okay, and then pKa, and then Ka. You need to relate. Yeah, you need to relate. So this one is done. Okay, it's done. Now, okay, let's actually move on. Okay, to the inclusion. Yeah, so this small part over here, I have put, okay, for the inclusion of Cl in carboxylic acid. Now we know, okay, we know that carboxylic acid is going to be the highest or the how to say, when you compare the weak acid, this is going to be a very good weak acid. Yeah, very good weak acid. So what happens if I have this weak acid, okay, when I include Cl in carboxylic acid? For example, okay, if I have carboxylic acid like normal, okay, like this, okay, and then we attach with CH3, okay, we have learned that, okay, the electron, okay, will be pulled towards the oxygen, okay. We have learned that the electron will be pulled towards oxygen, okay, and they are going to have the electrons to be delocalized between oxygen, carbon, and oxygen, okay. So that is going to make the bond between the O and H to be broken. Yeah. So this one no need to show the arrow, but I'm just showing over there that is going to be the bond that is going to be weakened and broken. Now, if I replace one of the H over here, okay, with Cl, okay, with Cl, what will happen? Okay, so do remember Cl is going to be also electron withdrawing group. So they are going to further withdraw, okay, towards the Cl. So if they further withdraw, okay, because the more the withdrawing happens, okay, it means that the delocalization will become more, okay, greater. Okay, when the delocalization becomes greater, it means that the bond, okay, between the O and H is going to be easily broken. Okay, so it means that, okay, if I compare, okay, let's say I write it over here. If I compare a normal carboxylic acid with CH3, and I compare with C double bond O, OH, with 1 Cl, okay, and then 2H, what will happen? Okay, this particular carboxylic acid, okay, the pH, okay, is going to be lower, or you can say the Ka is going to be greater, more acidic, or you can say pKa is going to be lower. So in simple terms, it's going to become more acidic. Okay, more acidic than what? Okay, than the normal carboxylic acid. Yeah. What happens if I replace, okay, with another Cl? Okay, the electron withdrawing effect is going to be greater. They are going to pull some more. Okay, when they pull some more, okay, towards the Cl, okay, what happens? Okay, they are going to further weaken the bond, okay, the OH bond. Okay, when that bond is going to be weakened, okay, we are going to have, okay, the H plus to be formed much more easily. Okay, so that is going to be another part. Okay, so it's not shown again. Okay, let me share the screen again. Okay, just wait for a while. My iPad is disconnecting. Join again, yeah. So you should get an idea. The more Cl is being added over there, okay, they are going to withdraw the electron, making that carboxylic acid to become more acidic. Yeah, I don't know why I cannot join my iPad. Yeah, hold on. Okay, my Wi-Fi. Kristen, okay, while waiting for me to connect again. Continue again. Yeah. So I was talking about, okay, the carboxylic acid is going to become more acidic, yeah, when you attach the Cl. So the same thing, if you have two Cl, okay, what will happen? The withdrawing of the electron is going to be much more greater, okay? So it will make the carboxylic acid now to become more acidic than the previous one, okay, which is going to be the pH will be much more lower, Ka is going to be higher, pKa is going to be lower, okay. So this is going to be, if you want to arrange, okay, then if you have another Cl over here, if I change, okay, if you have another Cl, okay, there will be more electrons is going to be withdrawn, so that is going to make, okay, the delocalization, yeah, of the electron is going to become more, yeah, between the carbon, oxygen, and oxygen, yeah. So that is going to make that ion to become more stable, yeah. So that will weaken the bond between the OH. So you are going to get, okay, more acidic, okay. So Cl, Cl, C double bond O, OH. So this is going to become more acidic. Okay, more acidic. So this is going to be pH is going to be lower some more, Ka is going to be higher, pKa is going to be lower. If I want to actually put them in order of acidity, yeah, in order of acidity, the one that is most acidic is going to be this one, okay, followed by this, okay, followed by this, and then followed by the last one, the normal carboxylic acid, yeah. So that is going to be about the acidity, okay, involving inclusion of carboxylic acid, yeah. So just to make it a little bit easier to see, maybe yeah, you can see. That is going to be about inclusion of carboxylic acid. Now, if you go further, okay, then after that we have learned about, okay, we learned about oxidation of carboxylic acid. So generally, okay, in the previous lessons, okay, we learned that primary alcohol, okay, they can be oxidized to become aldehyde, and aldehyde can be further oxidized to become carboxylic acid. And we learn in AS carboxylic acid cannot be further oxidized, yeah. But now you need to change that a little bit, yeah. But anyway, secondary alcohol, they get oxidized to become ketone, and tertiary alcohol don't get oxidized, okay. And the oxidizing agent that we use, yeah, for oxidizing alcohol to aldehyde carboxylic acid or secondary alcohol to ketone was acidified potassium manganate and acidified potassium dichromate. And the color changes, yeah, the color changes is going to be purple to colorless, and this one, the color changes will be orange to green. So these are the oxidizing agent that we use, okay. But in our syllabus, okay, for oxidation of carboxylic acid can be oxidized, but there are two types of carboxylic acid that can be oxidized, which is, okay, methanoic acid which is going to be a very good, strong reducing agent. Yeah, it means they can be oxidized easily. Yeah, methanoic acid, and then we have ethane dioic acid. Okay, ethane dioic acid. So if you look at it, yeah, methanoic acid, okay, can be oxidized by all, okay, strong, okay, strong oxidizing agent, okay, they can be oxidized by even the mild oxidizing agent as phthalate and toluene. Now, if you recall about phthalate and toluene, yes, phthalate and toluene we use, okay, to differentiate, okay, aldehyde and ketone. Yeah, ketone cannot be oxidized, so therefore phthalate and toluene normally we use to test for aldehyde. Okay, why? Because aldehyde can be oxidized to carboxylic acid. Yeah, it's a positive test for aldehyde, so we can differentiate them. Okay, but okay, the same thing you can actually use for phthalate and toluene for methanoic acid, because it's still going to give you a positive reaction. But you need to understand, yeah, what is phthalate. Yeah, recall back. Phthalate is going to be copper 2 plus ions in ammonia solution. Yeah, so copper 2 plus ion, okay, they are going to change into copper 1 oxide. Okay, so copper 1 oxide is going to be a brick red precipitate. Okay, so the presence of brick red precipitate is going to indicate that, yeah, the oxidation is happening. So methanoic acid do give you brick red precipitate. For tolerance region, yeah, tolerance region, we are going to use silver 1 ion. Okay, and you are going to actually this silver 1 ion, they are going to change into silver. Okay, they're going to change into silver. Okay, think, am I disconnected? Okay, anyway, I'm back. Yeah, so silver ion, okay, silver ion, they are going to change into silver. Okay, so silver, okay, the if you look at what is going to be the positive result, yeah, so it's going to be you have the formation of silver mirror effect. Okay, silver mirror will be formed around the test tube. Okay, so just to make it easier to see, okay, I will just put, maybe I'll use this. Okay, so this one, purple to colorless. Okay, if you have orange to green, if it is positive, then you are looking into brick red precipitate, and then here is silver mirror. Yeah, now all these four, okay, is going to be available for methanoic acid. Yeah, methanoic acid, because methanoic acid, okay, can be oxidized. Okay, and you need to know, okay, they will be oxidized to what? Yeah, methanoic acid, this is going to be methanoic acid. Okay, so only one H. So when they get oxidized, okay, you need to know, okay, there is carbon. So carbon, they will go out in form of carbon dioxide. There is hydrogen. Hydrogen is going to go off in form of water. As simple as that. Only one carbon, so one carbon. And the hydrogen, you have two hydrogens. So you have total of 3 oxygen. So 3 oxygen is already balanced. So you no need to worry about balancing. Yeah. So this is the equation. Okay, the equation that will happen. Now, for ethane dioic acid, yeah, ethane dioic acid slightly different. Ethane dioic acid, okay, they require strong oxidizing agent. Okay, they require strong oxidizing agent. Why? Because they have two groups of COH. Okay, they have COOH over here, two groups. So they need a stronger oxidizing agent. So ethane dioic acid will happen with KMnO4, ethane dioic acid. So it will happen with this. It will happen with this, okay, K2Cr2O7, but it will not happen with this too. Okay, so I'll just put it, okay, it will not happen. I put it over here. Okay. So what will happen in terms of equation? Let's look at the equation. They are going to give us, okay, same here, carbon. If you have carbon, they are going to give you carbon dioxide and they are going to give you water. So how to balance? Okay, you see you have 2 carbons, so you just put 2 there. Hydrogen, you have 2. So now you just need to balance the oxygen. There are 5 oxygen on the right. So if you look over here, there are 4 and 5. It's balanced already. So no need to worry about balancing. Okay, so this is going to be the oxidation of the 2 carboxylic acids. Okay, oxidation. Okay, done. Okay, now let's actually move on to acyl chloride's reactivity. Okay, so I hope you are still with me. Okay, now acyl chloride's reactivity. Yeah, if you look, normally when they say reactivity, they are comparing. Yeah, they're comparing the reactivity between acyl chlorides and the carboxylic acid. So they are comparing between these two. So in order to look at it, you need to look at the structure C double bond O. Okay, and then this is acyl chloride. Okay, this one normally R group. Okay, and then carboxylic acid, you have R group C double bond O and then OH. Okay, you have OH. And if you look over there, okay, you know that the electrons, okay, are going to be withdrawn here. It's going to be withdrawn over here. Okay, and if you look over here, okay, they are going to withdraw the electrons over here. Okay, they withdraw the electrons over here. This is going to make it more partial positive over here. Yeah, now what happens over here is the tendency of the ion that is going to be formed. Okay, you can see they are going to form some sort of carbocation over here. Yeah, a carbocation is formed. But if you look over here, they are going to form C double bond O minus. That is going to be the tendency of the ions that is going to be formed. Okay, but for the reactions, okay, the reactions are all involving, okay, attack of nucleophile. Okay, attack of nucleophile. They are not going to involve attack of electrophile. Therefore, they like the reaction because you have nucleophiles. Okay, so the nucleophiles have tendency to attack the delta plus. Okay, so they don't go and attack this one. So therefore, okay, most of the reaction, yeah, for the carboxylic acid, okay, it's better to react with acyl chloride because it is much more reactive. Yeah, because the delta plus over here is going to be the added advantage for the reaction to happen. Okay, therefore, okay, that is going to be about the acyl chloride. If you want to explain more, yeah, because of the withdrawal of the electrons towards the oxygen, towards the Cl, that is going to make the carbon to become more partially positive. Okay, that will be available for the attack of the nucleophiles. That is going to be the answer. Okay, now the reactions of acyl chlorides. Okay, the reaction of acyl chlorides, we have five reactions actually, but in total we have 4 if you combine the alcohol and phenol together. Yeah, so we have water. Okay, the reaction is called hydrolysis. Okay, the reaction with alcohol or phenol is going to be esterification. Okay, this one, number 3 and number 4 is almost the same. Yeah, because you are going to form amide. Okay, formation of amide. Okay, so you need to know, okay, what is the equation and so on. Okay, but this one, okay, they have given, okay, if you have R C double bond O Cl, okay, when you react with HZ, okay, they have given a general formula. You are going to get R C double bond O, okay, and then you have the Z over here, and then plus HCl. This is the general formula that they have given. So if you react with water, so it means they are reacting with HOH, okay, alcohol ROH, phenol, okay, this one, okay, and then I put OH, and then ammonia, okay, NH2, then I separate the H, easier to see that way. Amine, okay, NH2, then this one is CH3, So I just need to separate one of the hydrogen. So maybe I separate H and another H here. Okay, so now if I want to write the equation, let's say for example with water, let's look into hydrolysis reaction. Now this hydrolysis reaction, okay, happens at room temperature. Okay, you do not need to have any catalyst, no need to heat up. Okay, just with room temperature, okay, it will happen. Okay, it will happen because acyl chloride is very reactive. So if I put RC double bond OCl with HOH, what will happen according to the formula? Okay, you are going to get RC double bond O. Okay, the OH will come here, and then you have Acyl. This is the you are changing it into carboxylic acid. Okay, you are changing it into carboxylic acid. So this is going to be the hydrolysis reaction. Yeah, and it happens at room temperature. Okay, room temperature, no need to heat up. Yeah. Now, if you have the reaction with alcohol, okay, if you have the reaction with alcohol, then C double bond O Cl R. Okay, when you react, let's say for example ROH. Okay, the H, okay, is going to actually go out. Okay, so you are going to get RC double bond O, then the O and R. If let's say this is R1, this is R2, so R1, R2 plus, okay, HCl. So you are going to get ester. Okay, the difference of this, okay, is going to be you are going to react this at room temperature. Okay, no need to heat up. Okay, no need to use catalyst. Okay, but okay, if I compare these two reactions, okay, these two reactions with a common reaction, like for example carboxylic acid, for example, okay, or let's say reaction of this with carboxylic acid. Okay, if I compare esterification using carboxylic acid and alcohol, it requires, okay, I just put carboxylic acid over here, carboxylic acid, it requires heat under reflux, okay, and you require acid, which is going to be concentrated H2SO4. You require that with carboxylic acid. Why? Because it's not that reactive. Okay, it's not reactive. But now this one with room temperature is reactive. Yeah, it's reactive. Another thing that I can explain similar to carboxylic acid is going to be this reaction. It's called hydrolysis reaction, the first reaction. This hydrolysis reaction actually happens, okay, for halogenalkane. So if you have, let's say, for example, CCl, okay, CH3Cl, the hydrolysis, okay, this one, remember, it is going to be neutral water, okay, but the hydrolysis of halogenalkane, okay, they are involved not neutral water, they require sodium hydroxide. They need catalyst, okay, they require sodium hydroxide in aqueous condition. Okay, they require in aqueous condition. And what will happen, okay, that is the time where, okay, the HCl, okay, is going to be the HCl, this one and this one will come out, and you are going to get, sorry, that's the time that the OH will go in, sorry, the OH will go in. So you are going to get CH3 and then OH, okay, and then you will get NaCl, okay. So this reaction is going to be also known as hydrolysis, okay, if you compare. Okay, just I put like this. If you compare, it's also hydrolysis, but the difference is you need to heat under reflux, and you need to use sodium hydroxide. Okay, so in this case, you're just using room temperature. So what does it tell? It also tells that acyl chloride is more reactive than halogenalkane. Okay, so that is going to be the explanation. Okay, now if you look at it also, there is a part of this chapter saying that they ask you to compare, yeah, halogenalkane, you compare with acyl chloride, and you compare with this one, chlorobenzene or bromobenzene, if you compare, okay, which one, okay, will the bond, okay, between the carbon and Cl will be easier to be broken. Yeah, the one easier to be broken. So if you look at it, it's going to be quite easy to identify, okay, because, okay, if you look at acyl chloride, okay, acyl chloride, if I make it bigger, okay, acyl chloride is number one. Why? If you look at acyl chloride, if I have CH3 over there, it is pulling the electron over there, it's pulling the electron over there, okay, and this is going to make, okay, the bond between the basically this is going to be delta positive, the bond between the Cl is going to be broken. Yeah, so it's going to be still, the bond energy is going to be weakened and going to be broken. Now if I compare this with halogenoalkane, CH3 and then Cl, so if I redraw this, okay, maybe I put C H, then I just put another CH3, is still okay. You see electron donating group, okay, electron donating group, they will actually pull the electron and electron is going to be donated over here. So what happens, okay, the bond is going to be broken. Yeah, still going to be broken, but not as easy as this one. Okay, not as easy as this one. So it's going to be followed up by halogenoalkane. But the last one that is going to be broken is going to be this one. Why? Okay, because, okay, the Cl, do remember Cl, just like I told you, is an electron withdrawing group. Okay, but when it comes to benzene, yeah, they are going to be the electron is going to be overlap. The lone pair of electron is going to overlap with the pi bonding system. Okay, when there is overlap, okay, what happens? Okay, they will give you a double bond character, okay, between the carbon and Cl, making it less available for to be broken. Okay, therefore the bond energy between the carbon and Cl is quite high. Yeah, in comparison with halogenoalkane and acyl chloride. So that's why they will come at position number 3. So if you want to compare, okay, the reactivity or ability for them to react, yeah, you can see acyl chloride will come first, followed by halogenoalkane, followed by the chlorobenzene and so on.
This is for nucleophilic attack, right? But if it's electrophilic attack, it's like the other way
Yes.
around.
If it is electrophilic attack, you no need to even worry about halogenoalkane because halogenoalkane will undergo nucleophilic substitution reaction. And then acyl chloride, okay, they will undergo the reaction that we are going to discuss, addition, elimination reaction. But when we are talking about electrophilic substitution, then you compare with other compounds. Yeah, the other compounds, whether, like, for example, if the other compounds, like if you have the Cl over there, I want to compare the reaction with CH3, and then I want to compare the reaction with the OH. Okay, do remember, okay, when I see reaction, yeah, what kind of reaction we are talking about? Okay, the Cl generally, okay, they are going to donate the electron, okay, and then the effect, okay, of chlorobenzene doesn't have a very strong effect, okay, for the reaction to be very the reaction to be very vigorous. There is not mentioned in your syllabus, but for these two, yes. Okay, for CH3, these two are almost similar because they are donating the electron into the system. So the one that is going to be, this one's still going to be heated in certain cases. Yeah, still going to be heated in certain cases. But for phenol, okay, remember I told you, phenol is going to be electron donating group where, okay, the reaction between, the HNO3 is going to be even with dilute condition. Yeah, the reaction without the concentrated HNO3. Yeah, without concentrated sulfuric acid, they can still react. Yeah, under dilute condition at room temperature, so they can still react. the reaction with Br2. They can still react without the presence of AlBr3. Yeah. So all these, okay, are going to be special part, yeah, for this compound. So this one we leave it over here. Okay, that is going to be different mechanism. So now we come back to this mechanism, okay, the mechanism which is going to be involving addition elimination reaction. Now for the addition elimination reaction, I will show you, okay, the reaction involving water first, okay, then I will show you involving alcohol, okay, but I'm very sure if you know these two, you can deduce about how to use the amine and how to use ammonia, no problem. Yeah, so I'll show you the mechanism. Okay, so let's say we are talking about an one acyl chloride, so C double bond O Cl, let's say this is going to be CH3, okay, and I'm going to react with water. So first, okay, the electron will go this side, okay, delta negative. The electron will go here, delta negative. This is going to make this one delta positive. And I will bring, okay, the water over here. And we know the water has two lone pairs, so the lone pair will go and attack the carbon. Okay, when they attack the carbon, okay, what will happen? You are going to have the one of the bond went over there, so you become negative. The Cl still, the reaction is still there. And then this one O, okay, H and H, because the electron went inside the carbon, so it's still positive now. And then you have the CH3. So next step, okay, is going to be this one is not stable. So the electron, from the negative, they come over here to try to form the double bond again, okay? And then this bond between C and Cl will be broken. And this one, okay, the electron from the O and H will go and donate the electron towards the O, and that will give you the H plus and Cl minus. So you will get HCl, and the product is going to be, you are going to get C double bond O, and then OH, and then CH3. So this is going to be the product, okay? So this is going to be the overall reaction with the hydrolysis. Yes?
Could you explain the second step again just now of the hydrolysis?
This one?
Yeah, the middle one.
The middle, okay. So if you look at the middle one, yeah, you can see that, okay, first, okay, because the electron from the double bond over here, they went towards O, okay, so it means it will become negative charge, okay. And then this reaction is still ongoing. We didn't break it. Yeah. So what happens? This one, the negative, the lone pair, they try to actually come back again to form the double bond. Okay, they're not stable. And then the bond between C and Cl is going to be broken. Yeah, because Cl is pulling the electron. And then the electron from OH over here, okay, they will come towards the O plus, okay, to make sure it is neutral. So during that process, the bond between O and H is broken. So what will you get? Okay, the Cl bond is broken, and then OH bond is broken. You get HCl. So what is left? Okay, you have the double bond being formed, and then you have OH, and then you have the CH3. Okay, if you look at it, okay, I will actually redraw this again for alcohol. Okay, it's the same mechanism. Okay, let's say if I have C double bond O, Cl, and then CH3, and I am going to react with ROH. Okay, ROH. And we know the oxygen has the lone pair for the alcohol. Okay, it's not reflecting over there yet. Okay, but anyway, okay, while waiting, okay, it's a bit slow in my iPad. Now, the first thing, okay, that we need to put, okay, hold on. Let me try to share it again. So, I don't know what happened today for the iPad. What lesson you have after this? Ashley, what lesson you have after this?
Things. We have PPKN Bahasa Indonesia.
Okay. Now you see here, okay, alcohol, okay, the same, yeah. So this one, they will come over here, okay. This one, they will go here, okay. So this is going to be delta positive. This one will go here, okay. So you are going to get CH3, okay, C, single bond O, and then you have Cl still going there, delta negative. And then you are going to form, okay, with the O and then R and then H. Okay, so what happens, okay, the electron, the negative over here, they will come back to form the double bond. Okay, they will form the double bond. And then this is going to be positive because, okay, they donated the electron over here. So they are positive. So this is going to be compensated by these electrons. So what happens, okay, the bond, okay, between the Cl and H is broken. So you are going to get HCl. And the product that you are going to get is going to be CH3. C, the double bond is going to be O. And then you have O, and then you have R, okay? So this is going to be ester, okay? So similar reaction, okay, but the steps of the reaction is going to be, because the first one, okay, involves addition, okay, you add, and then the second one is eliminate, okay. So the same thing over here, you add, addition. What is going to be added? Okay, some the electron, yeah, they have electrons, so it's in nucleophile, yeah. So addition, and then this is going to be elimination. So in total, they are called addition elimination reaction. Okay, that is the mechanism. Now, if you compare, yeah, this one I went through already. If you compare the hydrolysis of halogenol alkane, okay, you compare with the hydrolysis of acyl chloride, it means we are talking about the reaction with water. Okay, for acyl chloride, there is a reaction with water. Yeah, for halogenol alkane, the hydrolysis happens with NaOH aqueous. Okay, and you need to heat under reflux. Okay, I have already explained just now. Yeah, I already explained. So this one happens at room temperature. Okay, why and so on, I already explained to you. Now, there is a question over here. Can this, okay, undergo hydrolysis? Okay, the answer is no. Okay, because, okay, the bond between carbon and Cl is going to be some sort of a double bond character. Okay, so because of that, because of the overlapping of the electrons to the pi bonding system, okay, therefore, okay, the bond energy to break the carbon and Cl is going to be very high. Okay, so there is going to be, they will not undergo hydrolysis. Okay, that is going to explain about. I think I went through this over here. Yeah. Now, reaction of acyl chloride plus phenol. This one also I went through with you, yeah, which is going to be the reaction with acyl chloride and phenol. Okay, we know, okay, that they can react with 5 things. Yeah, water, I show you the mechanism. Alcohol, I show you the mechanism. Ammonia, you did the example the other day. This one, amine, if you know about ammonia, yes, you know about amine. So the only thing that is going to be left is going to be the phenol. Now, phenol is going to be slightly different because phenol, okay, you need to have warm and sodium hydroxide in comparison to alcohol. Okay, alcohol, okay, when they react with acyl chloride, okay, you just need to have room temperature. Okay, no need to heat them up, room temperature only. Okay, but phenol, you need to warm and give sodium hydroxide aqueous because you need to form the phenoxide ion first. Okay, you need to form the phenoxide ion. So you cannot just simply use like that. Okay, if you have, let's say phenol. Okay, if you have phenol, okay, don't react phenol, okay, with carboxylic acid. Because why? Carboxylic acid and phenol, they don't react. Now, this is very important. Okay, carboxylic acid and phenol, they don't react because phenol is unreactive, carboxylic acid is unreactive. But that doesn't mean unreactive in what sense? Okay, this is reactive when it comes to electrophilic substitution. But this reaction now, we are not talking about electrophilic substitution. We are talking about nucleophilic, yeah, nucleophilic, in this case, addition elimination reaction. So we are not talking about that, yeah. So this is both of them unreactive, so they are not going to react. Okay, 2 more minutes. Okay, let me actually write down for you. Okay, first, okay, phenol, okay, they are going to react with sodium hydroxide. Okay, they are going to give you sodium phenoxide, O minus and A plus, and then H2O. Okay, so this is going to be, okay, the nucleophile, okay, that we want. Okay, we create the nucleophile and you need to warm this, yeah, you need to heat up. Yeah, once you get the nucleophile, okay, you can react, okay, with the acyl chloride. So if I have RC double bond OCl, I react with this phenoxide ion, O minus. Okay, we know that this one is going to be negative, this one negative, so this is going to be delta positive. Okay, if that is delta positive, we know that this one will come and attack the carbon. Okay, they will come and attack the carbon. So you are going to have, okay, RC, okay, O minus, okay, and then Cl still. And then once they attack, you get O, you get this. Okay, and this is carbon, okay, and there is hydrogen over there. So this is going to be positive. So what happens over here? Okay, the bond, okay, over here between the oxygen, this one will go over here, okay, give out the hydrogen. So you are going to get, okay, you are going to get ACl, and you are going to get RC double bond O. This one will go back. Okay, and then you will get O and this one. Okay, you will get the some sort of the ester, yeah, which is ester, not some sort of ester, it is ester. Okay, this is going to be the final reaction, yeah, in terms of mechanism. Okay, in terms of mechanism, but it's going to be, you need to include this additional step, yeah, which is going to be production of phenoxide. So what type of mechanism is this? Again, this is going to be addition elimination reaction. So now, Okay, I included all these are not inside your textbook. You need to learn, yeah, how to apply. Yeah, so this is the first time I draw this, okay, but it's all coming back from the mechanism that we have learned earlier. Yeah, so yeah, so this is going to be the entire chapter. Yeah, I thought I can finish earlier, but I did, okay, quite slow.